All right, we're going to go over the basics. This is the very foundation of talking fiber testing. So to get an understanding of what an OTDR is doing, we need to understand some principles with physics. I didn't pay attention in high school, so I've spent many hours trying to relearn all of this. And I want to share how I look at this information, and hopefully it helps you guys out. If you got better analogies, let me know, and we'll share those as well. All right, so the internet. Where does it come from? Where does it go? Really, it's a whole bunch of spitballs is how I like to break it down. And ultimately, we have a person sending information to another person over here. And those people are getting hooked up by fiber optic cables, hopefully. Otherwise, maybe it's copper cables. But regardless, they end up getting connected by this medium. So what is that medium? In fiber optics, we talk about wavelengths, and there's all sorts of crazy different numbers you hear, like 1310, 1550, 1490, a lot of different numbers out there. So let's simplify this, all right? So right here is a pretty basic picture of what a single strand of fiber cable would be. So the very core of this, where the light is transmitting, is 9 micron, which is really small. A strand of hair is going to be about 60 micron. This larger surrounding part, this is called our cladding, and this is going to be 125 micron. The cladding and the core is just hugging the core. It's a slightly different glass, which is the miracle of fiber optics, the index of refraction. So what happens as light hits this border between the core and the cladding, it stays within the core. Go put a stick into a jar of water, and the stick looks like it gets bigger or bends. That's the index of refraction. That's what's happening as we shoot light down here. So, all right, let's take a step back on this now. In fiber optics, we have a power source. And when we're shooting a spitball, we have a power source. So when we're shooting a spitball, the power source is our lungs. All right, we're taking the air in our lungs and we're pushing it out as hard as we can into this straw. So the medium here, so the material that's holding this all together in this analogy is our straw. And the force right here, or the velocity, is the air. The air that is being pushed out of my lungs. We could look at it also as CFM or PSI if we really wanted, but it's air that's pushing that spitball through that straw. Now, what's coming out of this spitball, or out of this, is our spitball. So with this analogy, we have our spitball coming up. Now let's translate this to fiber optics instead of what I did in 7th grade. So what is the power source with fiber optics? A laser. So here is our laser. It's a pretty bad one. And so we hit the trigger, and this is injecting light into the core. So this is our power source, this laser. And that laser is shooting for fiber to the home with fiber cables. It's shooting into our fiber, which is a glass core. And what is the force? What is the force? What is actually pushing what the input is? What are we pushing with? Here we're using air. The air is pushing that spitball. In fiber optics, wavelengths. The force pushing our spitball right now is wavelengths. And we'll talk a little bit more about wavelengths, okay? But that's the velocity, that's the force pushing our spitball. We already talked about what the spitball is here, but what the heck is the spitball over here? Basically, the spitball that we're injecting here, this spitball that we're putting into this fiber cable, it's a packet of information. It's a bunch of ones and zeros. And these ones and zeros turn into www.mymillennium or whichever website you want to go to. So we shoot our laser. That's the power source. And it goes into the fiber cable. And that packet of information is being pushed by wavelengths, ultimately going from our CO central office over to our house. So our output is data or packets. Now, let's take this just one step further today, wavelengths. I want to talk more about wavelengths, because once you get this basic understanding of what is happening, we start talking about a whole bunch of different numbers, wavelengths. So for us, when we're talking testing equipment, wavelengths are critical. So we have different wavelengths traveling down this core. The most common wavelengths used within our industry are 1310 and 1550 nanometers. Nanometers is a measurement. And there's a couple other wavelengths out there that you're going to hear about, like 1490. When we're testing live fiber optics, often we're talking about 1625 or also a lot of times 1650 nanometers. All right. So somebody calls you up and they tell you that, oh, I need an OTDR and I need to have a live filtered port. And then you go to Expo and you say you need a live filtered port, and they're like, well, what wavelengths are you testing? You're like, I don't know. So I want to try to help you understand the wavelengths, and so we can help advise our clients on which equipment to choose and which options they may or may not need. So the wavelengths. We've got our laser, and we shoot that into this core, this 9-micron core. And when that light actually goes down there, it propagates. So it makes this wave over and over. And it's traveling at the speed of light going down the core. The distance from the top of this wave to this wave, this is a measurement. That measurement is going to be 1310, 1550, or 1650. That is the actual measurement from peak to peak. Now, since it's a measurement, that makes it a little bit easier to understand. If we had a wavelength that doesn't make as many bends and turns like this measurement is longer, so this is going to be a higher wavelength. This is going to be a 1550 as opposed to a shorter one, a 1310. All right, now we're going to try to connect one more dot here, going to testing. So 1310. Let's think of this as a El Camino. You're downtown, wherever, whatever urban city, you're downtown, you turn on a wrong road on an alley and you need to turn around. 1310, it's this really hyper wavelength. It's making a whole lot of bends and turns. It's going to be able to get through turns or dead ends a little bit easier, just like that El Camino. It's going to be able to do a U-turn and get through that alley just fine. Now, 1550, that's a little bit longer of a wavelength. That 1550, let's say that's a long bed pickup truck. Same scenario, it goes down that road and oops, I don't want to be here, I need to turn around. So that truck, it goes, say, hey, let's get out of here. It can't do a U-turn. It has to come to a stop and it has to do a Y-turn, and it's taking it longer to get out of a situation. Same thing. 1650, longer. It's going to take even greater distance for it to make these cycles. So from here to here is even a greater distance. So now we're at 1650 nanometers. This, let's say this is a 48-foot semi-truck. It's just parking. It's parking. It's going to wait till there's no traffic behind it, and it's going to try to back out. So these wavelengths have different principles while they're operating inside the glass. So as an operator of a network experiences errors, if there's a bad splice right here in this fiber cable, these wavelengths, they're going to lose some of the power that the laser gave to it. And if there's, let's say, a bend in this cable, our 1310 wavelength is going to go flying through there. It's El Camino. Whereas our 1550, when it goes through there, it's coming to a halt. So our OTDRs are able to figure out, hey, there's a bend in our cable. We've got a problem. Now this last wavelength here, 1650, most networks don't operate at that wavelength. Most networks are operating in these two windows. Those are the most common. You'll also hear about 1490, and if you hear about WDM wavelengths, they're very unfamiliar numbers, but they're going to be right in this range. They get close to like 1610. But with that being said, is as spitballs are being transferred back and forth all day long from the CO to the house to the CO, back and forth, they're communicating in different spitball language in 1310 and in 1550. But let's say that this guy is upset, he's not happy, he's got no internet, not happy. So he calls up the ISP, says, I can't stream my favorite show, or my grandmother can't do telehealth medicine right now. She can't make her appointment. Come fix this. So what their technicians are going to do is, there might be another 100 houses somewhere over here that's on this fiber cable. We don't want to just unplug or turn off their laser. So we send our technicians over to this house, and they're going to test at a different wavelength, at 1650. So this wavelength will not interfere with those other spitballs being transmitted. It will not get in the way or disrupt all the other people on their network not having issues. I hope this was a decent rundown on wavelengths, and you guys can walk away feeling a little bit better about it. Have a great day. Reach out to us if you need help.